All right, so let's now have a think about metal ions and flame tests and what is happening when we do a flame test. Now, if we go back to our structure of an atom, we know we have the nucleus here, and it's going to contain protons and neutrons. And we also know that electrons, basically, they do something like this. They don't do this, but what we're saying here is that there are stable energy levels for the electrons. That we call them shells. We could also call them orbitals, but it's probably better to steer clear of that word in this side because they're not, thanks. They're not really orbitals if you go on to chemistry. And this is where our electrons are found. Now, if I heat up my metal ion, what I can actually do is I'm giving it energy. Like heating something is adding energy into the system, isn't it? So it's a transfer of energy. Because one of our laws in science is the conservation of energy. We can't make energy and we can't destroy it, but we can move it from one place to another. And so when we heat something, we're moving energy into the metal ion, and the way that the metal ion responds to that energy is it excites its electrons. Okay? The electrons get really excited, and that allows them to jump up to a higher energy level. Now, quantum mechanics tells us that, and observation tells us as well, that electrons can't just sort of wander around in between. They have to go up to another level. It's sort of like climbing the rungs of a ladder. You can stand on each of the rungs of the ladder, but you can't stand in between the rungs. And so our electron can be excited up to a higher energy level, and it does that by accepting a packet of energy. Okay, so this is so that's how it goes up. We call this packet of energy a photon. And in the process of, it can't stay in this excited state indefinitely unless we kept adding and adding and adding energy. And so what happens is it will drop back down again. This is the part that we're pretty well interested in, is when it drops back down again, it releases a packet of energy the exact same size as it took in to reach the higher level. So here we are emitting a packet of energy. Okay, photon. When we drop back down to a lower energy level. And for some elements, this is in the visible spectrum. We can see it as colour, depending on the wavelength of that photon, that packet of energy. And each individual ion has a characteristic colour because of the geometry, if you like, of their ions. The wavelength that's appropriate for their electrons to be dropping back down are going to emit a certain wavelength of light. Okay, and so because each metal ion is unique, we can then, as I said, we could use this as a means of determining which metal ions are present in an unknown substance. We could do a flame test to see what's there. And if you look at on page 27, you can see there that there's quite a few colours. Not every ion emits in the visible spectrum, and so it's not a definitive way. You're like looking at the colour isn't a way that you can identify every ion, but the fact that elements do this means that we can test and determine the composition of things like stars. If we look to see what wavelengths are being emitted from stars, we can determine their composition. And it's this kind of thinking that's behind the analysis that is being done on Mars and other, like and the Moon. What's the composition of the rocks on Mars? Well, we check. We're not doing flame tests, but we're looking at exciting the electrons on the atoms present to see what spectrum they emit, and that way we can determine what's present. All right, and of course this is really important for fireworks, isn't it? This is how we get our colours in our fireworks. Now, this is just a